Hi everyone, welcome to the last video of the video series of the Introduction to Newton's Laws. So in this one I'm going to focus on Newton's third law. So we kind of know it already, as you know, for every action there's an equal opposite reaction. We could write it mathematically. Now when we're talking about actions, we're really referring to forces. So here you got force action is equal to the opposite. So remember, opposite in physics is a negative reaction. And what it means is essentially that there are always two forces acting in pairs in between two objects. So really this is an interaction of two objects, and the force that they feel between each other is the same. So here are some applications of that. So when we have an interaction, so in this case the interaction is going to be the earth and the rock. So let me, see if I can write here. Okay, cool. So, by the way, an interaction, an interaction is just a big word for, you know, what happens when two objects come in contact. And that's kind of what Newton's third law focuses on. So the first one we kind of focus more on just like what the object's doing in terms of its motion separately. But this one we have two objects. So notice that we have the rock here and the earth. Of course, the earth is just this big thing right here. So essentially what Newton's third law says that if the earth is pulling on so this is the earth on the ball right here. The reactionary force is going to be the pull from the ball on earth. Now the crazy thing about this is that the earth pull and the ball pull are the same. So that's really crazy. So that means anytime an object falls, the object is pulling the earth upward. So that's what Newton's third law means. And the pull is equal to the force. And they're both equal. So if this is pulling with 100 newtons, this is also pulling with 100 newtons. That's action-reaction. So if you take two force sensors, I'll demonstrate this in class because it's really cool to see. But a spring force looks like this. It's just this little device right here. It's got a little hook. And exactly what you might imagine, this measures a force. So if I put the two hooks together, like this, measuring force, we'll find no matter what we do on this side, this one will always measure the same amount, like in Tug of War. So no matter how much this side pulls, this side will always pull the same amount. Hence why Tug of War is so hard. So how do you win a tug of war, right? If you're pulling at the same rate, you have to create a net force. So you have to create, a way to change the motion when you do that. So force exists in pairs, but notice the formula, right? Tire pushes on road as much as road pushes on tire. So you're basically looking at the interaction of the tire and the road and the tire. So two objects, right? With two objects, we have two forces. And that's action-reaction. Rocket on gas, gas on rocket. Man on spring, spring on man. And notice that it's not spring on ground or spring on wall, that it's always between the same two objects.
Trinity Lee, if you're in the building, please come up to the main office.
So here's the idea. You have a bug and a bus, all right? And let's say you're driving and the bug comes into the windshield right here. Is the force the bug feels the same, greater or less? And does the resulting acceleration of the bug, is that the same, less, or greater than that of the bus? So to answer this question, it is the following. So even though we have this tiny little bug right here, the force that the bus pushes on this, according to Newton's law, is the same as the force the bug pushes on the bus. So those are the same values. But what we see are two different things, right? Even though they have the same forces, it's kind of amazing. What we see is that the bug, according to Newton's second law, force is related to mass times acceleration. So what's going to happen is the force on the bug has to equal the force of the bus, which means the mass of the bug times A of the bug has to equal mass of the bus, A of bus, just like that. But what do we know about the mass of the bug? It's teeny tiny. And what do we know about the mass of the bug? It's super big, right? So in order for these to equal out, that means something else has to give, which is the acceleration. So to balance the big mass here, there's got to be a big acceleration for the bug and a small acceleration for the bus. And that's why we have the bus doesn't change its motion very much, the acceleration, because the mass is so big. Whereas the bug does, the bug splats. The acceleration's pretty great. So what we see is we have two things interacting with the same force, but different accelerations due to their mass. And that's kind of what I'm talking about here. And this is me doing the same thing just in another way. F is the same, and to counteract the differences, we have to adjust for 1. So there's a hypothetical question. So say there are birds in here. These are birds. Just go with it. I know they don't look like birds here. So kind of the same question, you know, if you have birds flying around in the truck and you weigh that truck on a scale, does it weigh less than if the birds were sitting down at the bottom? And the answer to that is that it weighs the same. Which is pretty crazy, but action-reaction. When the bird flies, it has to push in the air. Well, that push has to go somewhere. It pushes on the air, and the air pushes on the ground. And that's in order for them to get flight. So with that push, we find that the truck actually weighs the same amount because we have action-reaction here. So MythBusters does like this whole episode on it, which is pretty miraculous. So, in essence, what we have is this last note right here, is that objects, anytime they have contact with another object, they'll always feel a force, and the magnitude of that force is always the same. They're just in opposite directions, hence the action equal opposite reaction. Just like that. And you'll have force pairs in the system, so they're always between two objects of the same objects. And there's always two forces that describe an interaction. This is different than net force. Net force is one object, because when we do a net force, we look at just one object and all the forces acting on that object. So this can be more than, but not limited to, two forces. So that's the difference between action-reaction and net force. Net force, one object. Action-reaction, two objects, like that. But again, we're going to use all three of these laws to model our motion. So that concludes our intro to Newton's laws. So using all of these laws that we have right here, we can describe an object's motion. So let me just do one quick example of that. I wonder if this shows up. No. We're going to discard. So let me just do a new slide so I can show you how we can use all three laws. So all three. So say we have, sorry, I'm kind of in the way, but say we have an object falling. Okay? So when we model fall, it's the force of gravity only. So how does each of the three laws describe what's happening here? Well, the first law says an object in motion will stay in motion unless there's an outside force. So we know a falling object does accelerating. A falling object accelerates. So because this object is accelerating, there must be an outside force, or a non-zero net force, which is exactly what we have here. This thing in free fall, we say that's an acceleration. So Newton's law, first law, checks out. Now the magnitude of the net force can be modeled by the mass of the object times the acceleration. In this case, the acceleration is the acceleration due to free fall. So this is how we can use Newton's second law here, where we have the rate of the acceleration and the magnitude of our force. And then lastly, what we have is the Earth and the object. So this would be right here, the pull from the Earth, so Earth on object. And we know by definition there's going to be reaction force, object on Earth. That's present on the system. But more importantly, even though we have the same magnitude of the forces, we see an acceleration on the object here because the mass is way less than the mass of Earth. And vice versa, we don't see the Earth accelerating because the mass of the Earth is way, way, way more massive than the mass of the object. So little to no acceleration. So that's why we see what we see. So as we go through this unit, we're going to go through all of these laws kind of throughout the whole year, actually. Of course, we'll focus on them through this unit, but we'll be able to use them to describe motion.